Imagine two brilliant developers looking at the exact same dataset, the exact same codebase, and the exact same model. One looks at the output and sees a breakthrough ready to ship. The other looks at the exact same numbers and sees a system that might fail catastrophically the moment an anomaly hits the tail distribution. Both are equally intelligent, and both understand the mathematics involved. The difference in their conclusions has nothing to do with technical skill. It is entirely a product of their cognitive framing. This diagram represents a point estimate. A point estimate is a single value, like an average or a predicted return, used as a best guess for an unknown outcome. Our instinct is to crave this kind of certainty. We rely on these single, decisive numbers because they make a chaotic world feel manageable. But in complex systems like finance or artificial intelligence, treating a single number estimate as an absolute truth creates a dangerous blind spot. Relying on the illusion of certainty leaves us exposed when reality inevitably shifts. To navigate these systems, we have to look past the top-line numbers and understand the mechanics behind them. Quantitative thinkers don't treat numbers as final answers. They look past the specific value to examine the structure of the system that produced it. This diagram shows the trap of the average. Here we have two distinct distributions of data that share the exact same vertical centerline. Two systems can have identical averages, but deliver opposite lived experiences. One strategy delivers small, steady gains, while another fluctuates violently. On paper, the average outcome is identical, but risk profiles are worlds apart. Real danger hides in the distribution tails, those extreme outer edges where rare, catastrophic events occur. Our natural instinct is to speak in absolutes. We want to say a strategy works or a model is safe, but quantitative reasoning demands conditionality. Conditionality is the mathematical reality that the probability of an outcome is explicitly dependent on a specific set of environmental assumptions remaining true. A model that performs beautifully in one set of circumstances will quietly degrade and eventually break the moment those underlying conditions shift. An average is merely a summary. If we ignore the mathematical context surrounding it, we remain blind to the actual risks embedded in the system. While most people want to defend a successful idea, a quant's first instinct is to aggressively interrogate it. They maintain an adversarial relationship with their own work. Instead of seeking immediate confidence, they hunt for hidden dependencies or fragile assumptions that could lead to failure. This visualization shows the process of testing extreme edge cases. By feeding a system unusually massive or tiny inputs, quants force the model to reveal how it behaves at the limits of its design. Breaking the system intentionally allows us to find all the fractures before reality does the damage for us. Uncertainty is not a paralyzing problem to be solved. It is the default state of the universe. To handle overwhelming complexity, quants use decomposition. Decomposition is the mathematical strategy of dividing a massive system into smaller, manageable components to understand how each piece functions individually. By isolating these components and assigning them expected probabilities, what once looked like an unsolvable mystery becomes a structured, navigable landscape. By actively breaking our ideas and structuring the unknown, we transform uncertainty from a void into a strategic advantage that allows for confident decision-making. This mathematical approach doesn't replace human intuition, it sharpens it. It creates a feedback loop where intuition spots a potential pattern, and formal reasoning determines whether that pattern actually holds up to the data. These habits aren't just for building algorithms or trading stocks. They are a framework for making better decisions in any environment where the future is unknown. Once you step away from the need for perfect certainty, you can begin to see the world as a complex system waiting to be mapped. Thinking like a quant means numbers are never the end of the conversation. They are the specific evidence we use to understand the hidden architecture of the world.